All right, in this example, we're going to approximate values for the derivative of a function that's given in a tabular form. All right, it's given numerically, not as a graph or a formula. Now we're just given the function as a table, and we want to try to come up with values of the derivative. So this makes it's a little easier actually than being given a graph, because it's kind of tricky to draw those tangent lines and try to estimate the slopes of those tangent lines. We can find the average rate of change between any of these points, and we know that the average rate of change is related to the instantaneous rate of change, but there's no way to get points that are closer and closer together. We don't know anything about the function between, in this case, between 0 and x equals 0 and x equals 2, or between x equals 2 and x equals 4, right? We're only given these discrete points. But we're going to do the best we can. Let's first of all just calculate the average rate of change for this function over each interval that's given. Okay, so I can look at the average rate of change between 0 and 2. I can look at the interval between 2 and 4. I can look at the interval between 4 and 6. And I can look at the interval between 6 and 8. All right, we're just going to look at the average rate of change. So I'm going to take, for this first interval, I'm going to take 43 minus 110 and divide that by 2, right? It's 2 minus 0, right? But the change in x is 0. So what do I get? I get a negative 33.5. Okay. And the next interval, I'm going to take 30 minus 43, again, over 4 minus 2, which is 2. So negative 6.5. Next interval is 24 minus 30 over 6 minus 4, which is, again, 2. And that gives me a negative 3. And then I'm going to take 21 minus 24, and then 8 minus 6 is again 2. So that gives me a negative 1.5. All right. Now, at the endpoints, I really can't do any better, right? Because I don't have anything on either side of 8, right? I only have the one side. So I'm going to go ahead and fill those in, because this is as good as I can get for the endpoints. All right. Now, for the other points, let's actually kind of sketch what this thing looks like. All right. So if I were to draw a little sketch of this graph here, and let's see, it goes to 110. Let's see. Let's do 20, 40, 60, 80, 100. So here's 100. This is 20 down here. And let's do 2, 4, 6, 8. 2, 4, 6, 8. Let's kind of graph what this looks like so that I can show you how we can get a little bit better estimate for the points in between here. All right, so we have at 0, we're about 110. Let's say that's about 110. And then we're at 43, so 30, 43, so it's roughly here. And this doesn't have to be very, very good. So there's about 30, and then 24, and then 21. Let's just say it looks like that. Okay, this is sketching it, this graph. So if I want to, let me pick up another color here. If I want to find the tangent line at 2, right? That's something like around here. I'm trying to find the tangent line here. Oh boy, it's hard to sketch this. So there's a tangent line, right? Now I could actually, what I have is actually let's do that. I have this slope and I have this slope. And I know that the derivative at 2, right, the slope of the tangent line at 2 has got to be somewhere in between those two slopes, right? You can see that the slope is negative and it's becoming less negative, so it's increasing, right? It's concave up. You can see that the graph is concave up. And So you can see that maybe if I just average these two slopes, then I'll end up with the slope that I want. Okay, it's gonna be somewhere between those two. My graph is kind of small, but so what I'm gonna do is just average these two. So to find the slope at 2, or to approximate the slope at 2, or the derivative at 2, which is the slope of the tangent line, right? It's the instantaneous rate of change. I'm going to take the average rate of change between 0 and 2 and 2 and 4 and average them together, right? I'm going to take these two values and average them together. If I do that, I get an average of, if I put it in my calculator, I get a negative 20, okay? So I am going to actually say that probably a better estimate of the derivative at 2 is negative 20, right? So we can do that for these other intervals too. So if I want to find a better estimate, oops, that's a better estimate of the slope at 4, I can take the two slopes of the two those average rates of change, right? I can average the average rates of change and get a better estimate for the slope. Okay, so if I take the average of these two, 6.5 and or negative 6.5 and negative 3, if I just add them together and divide by 2, then I get 4.75. Okay, so I am going to say that a better estimate for the slope at 4 is going to be a negative 4.75. Okay, and I'm going to do the same thing with the next 2 points. I'm trying to find the derivative at 6. So the slope of the tangent line of 6 is going to be somewhere between the two average rates of change on either side of 6. So I'm just going to average those together to get a better estimate. All right, so I'm going to take a negative 3 plus a negative 1.5 divided by 2, and I get negative 2.25, just averaging those two values on either side. So I'm going to say that my best estimate for the derivative at 6 is about negative 2.25. Okay, now we couldn't do that at 6 and 8 because we don't have something. If I had 10, if I knew if I knew something about the value at 10, then maybe I could get a better estimate for 8. But you know, the endpoints I don't have values on either side, so I can't do the averaging trick to get a better estimate. But so that's as good as I can do given the information I have. Now I have a function for the derivative f prime of x in tabular form. I have it numerically. All right, I'll see you for the next video.